as Professor Rao suggested, I'll start off with a uh, apologies. Let me adjust my window here. Yeah. So he asked me to introduce myself as well, give a brief overview of my career and what I've done. So I've had the fortune to have spent the bulk of my career in the semiconductor and allied industries, except for these last few years. And I think something that the world is just understanding now is how critical these products and this technology is for everything we do in this modern era. Like semiconductors pretty much underpin all modern technology, whether it's the phones we hold in our hand, the satellites that are up in space, or the defense systems that keep us safe. And it's companies like Intel, KLA, Applied Materials, Apple, which are leading or have been and in many ways continue to be at the forefront of this technology, and where I've had the chance to learn the ropes of the industry and that have pretty much made me the engineer that I am. I've been away from the industry for the last few years, but now in my current transition, I'm looking forward to really excited to return to this sector and contribute in my way to the success of the Indian semiconductor mission. So it's an exciting time to be in semiconductors, even more exciting time to be in India and be in semiconductors. And we're all looking forward to the next few years and where they take us. So this is an outline of my talk. So why TSVs, some key applications, brief overview of design considerations, and then some time we'll spend on the process flows. Depending on how much time we have, we can go into one particular process flow in a little bit more detail. This information is all from public sources, so it may not be the latest or the most accurate in some cases. So please bear with me in that case and feel free to correct me wherever you feel that the information could do with some updating. So first of all, for those of us who might not be familiar with what a TSV is, right? A TSV essentially, as defined by Wikipedia, is a vertical electrical connection that passes completely through a silicon wafer or die, a through silicon via. What you see in this picture is two die that are stacked face to back and connected through these TSVs. So one thing immediately jumps to mind, right, is how large these structures are compared to the other device structures, right? So these are at scales of microns and tens of microns, in some cases, 100 microns or even more, right? And that is what makes them in many ways challenging to fabricate, challenging to integrate in conventional devices. And that's where a lot of work has gone into developing this technology, making it successful to where it is now rapidly being adopted in some sectors. So why TSVs? Like why go to the trouble of developing technologies, processes to make these big giant structures and insert them in die that have submicron or nanometer scale features with all the attendant complications and issues that could arise, right? Essentially, we all know that Moore's law, the law that has defined the semiconductors industry's growth and performance improvements over the last 50 odd years, is slowing down, right? That is what has made semiconductors smaller, faster, and cheaper. And now it is reaching its physical limits, as you can see from the graph to the right, where since 2012 or so, we are starting to see the actual gate length of transistors start to be bigger for the first time than the node that it represents. So that tells us that what we call 7 nanometers is not actually 7 nanometers wide gate. It is more and more becoming just a nomenclature to show that we are scaling from the previous generation to 10 nanometers to say 7 nanometers. So what it's also telling us is now beyond the raw processing power of the chip itself, the speed of the interconnection between the chips is now becoming more and more important to boost the device performance and to keep Moore's law going on in an indirect way. We need more than more, essentially, right? Power consumption, of course, we know needs to reduce, right? So you can see some examples here, like mobile applications, like a phone camera module, like MEMS devices, like that big NVIDIA server rack here. So this requires, to a large degree, reduction of, say, interconnect length or the mobile devices
Last year.
and in AI accelerators, right, where the data movement in the memory next to the GPU often consumes even more power than the computation that, say, the NVIDIA or the AMD GPU itself performs. So power consumption needs to come down. Form factors need to keep reducing, right? As we miniaturize devices, as we pack in more and more functionality into devices, the end device, whether it's the phone or the laptop, cannot become bigger, right? It has to stay the same size, or in some cases, even become thinner or smaller, which means if you have to stuff in more features into the same space, your form factors of your chips themselves need to come down. And that again requires, to some degree, minimization of interconnect length to create compact packages. And further, as we continue scaling, making devices smaller, fabrication of these small devices also becomes much more expensive. And that has led the industry to the realization that not all functions need to be integrated into a single die. And you can see that with this schematic on the top right, where for the same number of defects on a wafer, if you have a big die, your yield is 35%. Same number of defects on a or on a 20 by 20 millimeter die, yield goes up to 76%. And if your die shrinks by further factor of further factor of 2, the yield becomes 95%. So smaller dies imply better yield. So that's a very clear motivation. And also it reduces your fabrication cost at advanced nodes. Let's say functions that do not need to be fabricated at 7 or 4 nanometers can be fabricated on older generation technologies at lower cost. It also allows to reuse products from older generations and improved power and thermal management as a result. So what that means essentially is that separate dies can be fabricated and co-packaged to give you the same function that a big giant die would have been used for back before this disaggregation of functions started. One more feature, or rather one more reason that some of us might not be aware of is that there are physical limits to the size of the lithography reticle. It can only pattern up to a max size of, I believe, 850 by 850 millimeter. So your die cannot go beyond a certain size if it has to be made economically feasibly. So these things that you see on the right bottom are what are called chiplets, and how they're integrated is through heterogeneous integration. Different functions on a single substrate. So how do TSVs help here? They enable higher speed, lower power consumption, and a smaller form factor. So first and foremost, you can get extremely high interconnect density with through silicon vias. You can have a very, very high number of fine pitch connections and a shorter electrical path, as you can see on the image at the top right, where you have DRAM stacked using wire bonding versus DRAM stacked and interconnected through silicon vias. So here, with the wire bonding, you can see that the connections can be only from the edge of the die. So that inherently limits how many connections you can have. For through silicon vias, which are drilled through the entire silicon, that limitation is relaxed considerably. You can have thousands and thousands of connections. So that results not only in higher density of interconnects, also a smaller package size, lower power consumption, and of course, much higher data transfer speeds. And this power consumption is reduced through primarily by reducing the interconnect length, right? So that reduces your capacitance and gives you higher bandwidth per watt. And TSVs are used not just to transfer signals, but can also be used to transfer power. They are what are known as signal and power TSVs. So power TSVs also help reduce power consumption by reducing IR drop, voltage droop, reduce power supply noise, and, and through reduced RC delay. And through this massive parallelism that is enabled by having thousands of connections, you get drastically improved product performance. TSVs also enable this heterogeneous integration that we talked about, where you can have multiple types of chips on a single substrate in a package connected via high-speed connections, giving you not only better performance, but a smaller form factor. Because data transmission through TSVs and within a package is much, much faster than it is between packages. And we'll cover this in a little bit more detail in subsequent slides. Some key applications, right? So where are TSVs gaining adoption? Where are they adding value? First and foremost, this is the single biggest application and is also making the most news now, which is high bandwidth memory, or what's known as HBM, where you have multiple stacked DRAM memory die, which are connected via TSVs and microbumps. And the max size of the HBM stack ranges anywhere from 4 gigabytes to 64 gigabytes. HBM1, which has 5 die, which is 4 memory die and 1 controller die, and HBM4, the latest technology, which has 16 memory die and 1 controller die. So this HBM gives you approximately 10 times higher bandwidth compared to standard memory. And there is a specific application where these HBMs have gained huge adoption and which is pretty much driving their growth. So would anyone care to tell us what that application is? Any volunteers?
AI.
That's correct. So thank you. Essentially, HBM die, as you might not be able to see here, but we'll cover in some detail later, are co-packaged with GPUs for AI applications. This is because the memory is the bottleneck right now in AI compute. And these HBMs, through their high-speed data transfer between themselves and the GPU, enable much faster processing speed and, of course, manageable power consumption. And they are also able to manage the large current spikes that are generated during AI operations and other high performance workloads. And they're able to handle fluctuating load as well. So when an AI model is running, the power that it consumes is cyclical. It goes up and down as it runs and then stops between runs. So those kinds of transients can also be much better handled by this kind of architecture. And here you can see how the TSV looks in the HBM in a little bit more detail, right? So you have this is the through silicon via, and through solder and micro bumps, it is connected to the next memory die, and so on and so forth. And as you can see, AI since 2024 has caused HBM demand to explode. Higher bandwidth, lower latency, lower power consumption, single-handedly driving this massive explosion in memory demand. And you can see it in how memory prices have gone up, how the stock prices of memory companies have gone up as well. They are in huge, huge demand. In some ways, they are even more capacity constrained than NVIDIA and its fabrication partners are. So, and a little bit more detail on the AI, right? So these HBMs are heterogeneously integrated with logic on a single substrate. And the leading industry process, which pretty much all GPUs run through, is what is called TSMC's CoWoS process, chip on wafer on silicon. And NVIDIA is, of course, their biggest customer in this area. So this integrates HBM and logic on a single substrate. The HBM and logic communicate through fine wiring on this silicon interposer, and the interposer then has TSVs that connect it to the package substrate underneath it. And the latest generation of interposers that TSMC is making are also integrating more and more functions in the interposer itself, such as passive devices, such as high density wiring on small LSI chips. It's a little bit, from my perspective at least, like what Intel is doing with its EMIB technology, although I'm not well versed enough to make more than just an informed guess on that front. So this here is a silicon interposer. This here is a polymer, which is why you see separate silicon integrated in it. And these vias are not through silicon via, but they're still through vias. And this is an example of the NVIDIA Blackwell package, one of their latest product, and this is the GPU here in the middle, and these are 4 HBM stacks, delivering a total of 288 GB of stacked DRAM. It's a massive, massive number, right? Who would have thought, right? You would have 200, 300, close to 300 GB of DRAM on a single package. And if you look online, there is a rumor that the next generation will, in fact, increase the DRAM usage to 1000 GB, to a terabyte. So the scale is just mind-boggling, right? And none of this could have been possible without through silicon vias. Another application where TSVs have gained adoption is CMOS image sensors, right? So it's a very interesting technology. So this slide here shows the evolution from old first generation CMOS to backside illuminated CMOS to stacked CMOS, which is what uses TSVs. So you can see that in the olden days, the 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 light receiving substrate was below the metal wiring, which essentially constrained the efficiency or the quantum efficiency of the CMOS sensors. It was capped at around 50 to 60% because a lot of the light was scattered by the wiring, the interconnects. So the industry made the first big switch when they moved to backside illuminated CMOS, where the wiring was put below the light detection layers. So now your quantum efficiency skyrocketed to 90% plus, and it gave you much, much better optical performance. Angular light acceptance was better. It worked much better at low light in terms of signal to noise ratio. And the next logical evolution from here was stacked CMOS, where essentially what you have is the pixel layer. In between, there's a memory layer, and then there's a logic layer. So it's essentially disaggregated image capture and post-processing onto separate wafers. And they were connected via TSVs. And the TSVs enabled much faster readout. So images of moving objects, high frame rate videos, as well as much more powerful on-chip post-processing. And companies like, say, Apple, with or without the DRAM, have been using TSVs to connect the pixel layer and the logic layer for many, many years already, working with their partners in Sony. And here you can see a sample cross section of how it looks, right? With this, where you have the pixel layer, and in the periphery is where the TSVs are present, connecting the pixel layer through the memory to the logic layer. Now, these these applications are fine, right? But you can see, again, as alluded at the beginning of this talk, the design of these ICs has to be impacted by inserting these giant structures in between them, right? So some design considerations that are important that the industry has had to work around are electrical, physical, and reliability, right? So from an electrical standpoint, TSVs act as MIS capacitors. So that is a consideration. The copper resistance for high frequencies can become significant, and the inductance of the TSVs can also impact high speed devices. So that plays a role in where and how these TSVs are integrated into the design. Beyond that, there is a keep out zone associated with the TSVs to ensure that this interference, this interaction with neighboring devices is minimized or eliminated. So that takes up valuable real estate, of course, and is a critical design consideration to ensure these devices work as expected, not just at time zero, but throughout their life, which is where the reliability component comes in. So copper to silicon, the coefficient of thermal expansion is very, very different. So that causes a lot of stresses in the silicon. So that can not only shift the stress can not only shift the characteristic of neighboring surrounding transistors, it can also physically cause cracks, delamination, and other kinds of damage to the TSVs as well as to the devices around them. And some tools that the industry uses to manage them, some standard tools which have been used in the past in other layers as well, is they sometimes add dummy TSVs for stress buffering, to manage hotspots, and to keep heat sources away from. And one more design rule is to keep heat sources away from TSV so that they don't take that heat and transfer it to other parts of the IC. By the way, one function I forgot to mention during the application discussion was the TSVs are also very good heat sinks. They are good at taking heat away from the device. So not only in some cases they might actually generate heat because of the I square R losses, but in most cases they are also helpful at transferring heat away from the device, and those are called thermal TSVs. Now we'll spend some time on process flows. Just a time check. How much more time do we have, Kumar?
We have another 20 minutes.
Okay, good. Thank you. I think we can run through at least the high level fairly quickly. So process flows, right? So there are three high level process flows. Via first, via middle, and via last. And the name itself tells you what they are. Via first is where the TSV is found before any devices are created on the silicon wafer. Via middle is in the middle of the process flow after the transistors and the front end of line is done, but before the back end of line, interconnects are fabricated. And via last is, of course, where the TSV is done at the very, very end of the process, usually on a thinned or background wafer. This slide shows you at a high level how the flow looks like. I won't spend too much time on this right now, but I'll share the slides with the team. I'm with Kumar and Dr. Rao, and they can decide how best to circulate them. And anyway, this is all publicly available information, but at a high level, right? If you compare the three integration schemes, this is a summary table, right? So the via first allows you a very high thermal budget, which is an advantage because there are no transistors yet put down. So you can go to a much higher temperature without worrying about the impact on any devices. It also lets you use material like polysync, silicon, and tungsten, and and smaller via geometries. But its applications are relatively limited as of now. Via first has not gained much adoption. The process flow, which has gained the single largest adoption, which is gives you a good combination of slightly larger dimensions, slightly looser pitch, but at the same time easier to integrate process is the via middle flow, which is done between the front end of line and the back end of line. So it has a thermal budget of less than 400 C. Materials typically, 90% plus is copper, and the VR depths and diameters you can see there, roughly 3 to 10 microns and 30 to 100 microns deep. And the pitch is roughly 10 to 40 microns. And the applications are CMOS image sensors, logic to memory stacks, and of course, HBM, which we discussed earlier. And VR last is done after the back end of line at a much lower temperature, more like below 200 degrees typically. The VR material is copper. These are, of course, much larger structures because they have to work around the existing device, which is now completely fabricated. So they can only be put in certain locations. And its main use cases are heterogeneous integration through silicon interposers. So VR last is typically used where the fine pitch connections are done not through TSVs, but through newer techniques and cheaper techniques like hybrid bonding, like redistribution layers, which we will not cover in this talk, because those are talks in themselves. What we will spend a little bit of time now is the VR middle process flow. So which I've broken up into two parts, the TSV formation, which is on the front side of the wafer, and the TSV reveal, which is done on the back side of the wafer to make the VR truly a through silicon VR. So at a high level, you start by etching the TSVs, putting down an insulating liner. Sorry, were there any questions? Okay, I'll take that as a no. Then you put down a barrier layer to ensure copper does not penetrate through the VR sidewalls, followed by a copper seed layer for enabling the electroplating of copper that follows. And then you polish it down to leave the copper buried only inside the TSV. This is how the TSV is formed. And the backside processing, after the rest of the back end of line is done, essentially you take the wafer, attach it to a support wafer, thin it down on the back through grinding and polishing. Then you etch it using typically a plasma etch, selective etch to oxide where the TSVs are now protruding out. Then you cover it with a low temperature oxide and nitride combination, nitride plus oxide. Then you perform one more polishing operation, CMP, chemical mechanical polishing, which flattens the topography and exposes or reveals the TSVs. And that is and then you can either then continue with the bonded wafer on it and build up the redistribution layers, or you can debond the wafer and use it for whatever else that comes downstream. Any questions on this high level process flow? Okay, we'll dive into the details now, starting with TSV etch. So typically, the TSV etch is a plasma etch using what's called a Bosch process, which consists of multiple steps of isotropic plasma etching. By isotropic, I mean it etches in all directions, and sidewall polymer deposition. The plasma etching is done using SF6, and sidewall polymer deposition is done using C4F8. So the polymer is what coats the sidewalls and keeps the profile vertical. It does not allow the isotropic etch to go sideways and broaden the TSV. So the process, of course, is a lot more intricate than what I've described, right? But essentially, it enables deep, high aspect ratio structures with vertical sidewalls. So it's pretty much is the industry standard right now. And one key issue that the industry struggled with, at least in the early days, was formation of these scallops on the walls of the TSV because of this etch deposition sequence. And the scallops, if they are wide enough, large enough, and deep enough, can create shadow regions where subsequent liners or metal barriers or seed layers might not be able to cover. And then, of course, cause major problems downstream. So solving the scallops was a big challenge at the beginning of the TSV technology development. Next step is the CVD liner. So this uses a chemical vapor deposition process using the TOS precursor, and this has pretty high step coverage. By step coverage, essentially, I mean the ratio of the thickness of the layer on the sidewall or at the bottom of the trench, whichever is the worst case, divided by the thickness deposited on the flat surface of the wafer. So high step coverage means the thickness on the sidewalls and at the bottom is a lot closer to this thickness. Poor step coverage means you have lesser thickness deposited here on the sides and the bottom of the trench because of whatever reasons, physical or chemical limitations. So this gives you electrical isolation, right? You cannot have copper in the trench because that would now be directly in contact with the silicon and of course poison the silicon and not create a functioning device. So it gives you insulation. This is deposited, of course, at a low thermal budget, less than 400 C, and its thickness is typically a few hundred nanometers. Again, depends on the width and the depth of the TSV. And as the industry scales to smaller and narrower TSVs, people are considering alternative processes like atomic layer deposition, which gives you very, very conformal oxide and can give you good step coverage for very small dimensions. Next step is the copper barrier and seed layer deposition. So the barrier typically is the same as what's used in conventional back-end of line processes. It's a tantalum nitride sandwich layer. So its function is provides a diffusion barrier to copper, an adhesion layer between the liner and the copper seed that comes after it, and is roughly 10 to 100 nanometers in thickness. 100 is, and this thickness when I'm talking about is the thickness on the top surface of the wafer. And after that, you put down a copper seed layer, which gives you a conductive path for the subsequent electroplating step, because electroplating needs a conductive layer, higher conductivity than what the tantalum nitride can provide. Also a nucleation layer for the plated film, for the film to nucleate and grow, and to provide better adhesion to the barrier. And this film is slightly thicker than the barrier layer and is deposited using a physical vapor deposition process. Newer generations use what's called an ionized PVD process, which gives you much higher step coverage. Because conventional PVD or physical vapor deposition is a line of sight process. So that often results in very poor step coverage on the side wall of the trench and at the bottom. And if your film is too thin, then you will have inadequate coverage. Possibly some areas you will not have a barrier layer or not have a seed layer, which will, of course, destroy your process. If it's too thick, if your barrier layer is too thick, then you have higher resistance issues. And the ionized PVD process essentially generates a plasma between the target and the wafer, which ionizes the sputtered atoms and improves the film uniformity and the film coverage. And again, for next generation processes, people are considering migrating away from PVD to atomic layer deposition and new materials potentially like, say, ruthenium as well to replace tantalum or tantalum nitride. Questions?
Hello, Uday. This is Vikas from front of Inas. I was actually thinking about ruthenium, what you mentioned. And my question was, from ruthenium, do you see that ruthenium as an improvement in terms of the thickness that it can be used compared to tantalum nitride as a barrier liner? You see there a significant advantage? Because I asked this, because it's not so easy to plate on top of ruthenium. Yeah. And how do you see the process flow there?
So ruthenium is still under development, right? For TSV applications, it's not really taken off yet. So there will be challenges, of course, right? But gives you better step coverage and better uniformity, right? So if there are challenges I believe the back end of line, the metal layers in interconnects are already starting to use it to some degree, if I'm not mistaken. So I'm sure there is significant work already done, not at the TSV level, but in back end of line metallization processes to integrate ruthenium. Let me, we can connect afterwards if you like and go into this in a little bit more
Absolutely.
detail.
Absolutely. Yeah.
Yeah? Thank you. Thank you for the question. Any more questions? Great. Copper plating, right? So now this is where we fill the TSVs and actually completely form them. So copper, of course, gives you the electrical conductivity that you need, gives you high thermal conductivity, and has a very mature plating process, which is why it was selected as the material of choice. And the electroplating essentially has a few key process parameters: the current density, bath temperature, composition of the bath, and of course, what makes it work here and in all high aspect ratio processes is the use of proprietary additives. So three main types of additives used are suppressors, accelerators, and levelers. So what the suppressor does is, as its name suggests, it slows down or suppresses deposition on the top surface of and on the side walls. The accelerator accelerates the filling or plating of TSVs from the bottom, gives you a bottom up fill, as you can see here in the middle. This is exactly what is desired. The fill has to start at the bottom and go all the way up, while minimizing the amount that we deposit on the sides, especially on the edges, so that you don't end up forming seams or voids or pinching off, as we say, the TSV. Because if the plating on the side wall, at this corner especially, becomes too thick, it can physically block the influx of reactants and block the plating inside the via itself.
So Udayji, just can I a question?
Yes, please.
Yeah. So all these samples are basically from the same step or same sample, or these are different images from the different samples, first of all?
These are three different process conditions. So if you click, I have the
Yeah.
link here to the actual paper itself, right?
Okay.
For more details. But
Yeah.
this was a study on optimization of the plating process, where they use different conditions.
Okay. So if you look
Figured
at
out which,
if you look at this part, right, on the field, the copper deposition thickness is almost the same. See, I understand that these chemical additives, brightener, suppressor, and leveler, they are going to influence something like superfilling effect, right? But if you look at on the field, there's almost no deposition is taking place. So how do you ensure that there's on the field side, on the top side, there's no deposition taking place? How do you ensure that?
there will always be deposition, right? You cannot eliminate, because the copper
Right.
seed layer is everywhere on the surface.
Yeah,
So
but
the goal is not to eliminate it, but to
yeah, but
slow it down.
if you look at the the center picture, I mean I'm talking about the middle one, right?
Mhm.
At least from the visual, it appears that the thickness of copper is same.
So these are just representative images, right, to show the defect modes that you see of incomplete plating, seam formation or void formation versus the continuous bottom-up fill process. So I don't think this process is necessarily used in the industry, but this is public information, early available information. I used it as a nice representation on the same structure of a process that actually works versus a process that does not work.
Yeah, because from my personal experience, there's always deposition on the field, okay, which will be like polished away during the later stages. Yeah.
Yes, you are correct. That is exactly how it is. This is more just a representation from an old academic study to show, to illustrate what the point. Thank you for your input. It's
So,
very helpful.
Dr. Mahajan, this is your own work or this is you're taken from literature?
From literature, from literature.
Okay.
My own work is all proprietary to the companies I've worked at. I cannot, I don't have it because I don't work there anymore. I'm not allowed to take my work with me. And even if I had it, I wouldn't be sharing it.
Right. Okay, but it has been related to TSVs, is it?
For some years, I worked on TSVs. Yes.
Okay. Thank you.
At applied materials, right?
That's correct, Dr. Rao.
Yeah. Okay.
And wherever I've used these external sources, the links are there on the particular slide for those who would like more details about the image or the chart, as it may be.
Can you please share this presentation later?
Yeah. We'll do that.
Thank you.
Yeah.
Yeah. The last step for the front end, the via middle process flow front side is TSV CMP, as one of the questioners alluded to, just described earlier, which is chemical mechanical polishing, where this copper, what we call overburden, which sits on top of the structure, is polished away, removed. So you first remove the bulk copper. It's typically a three-step process. You remove the bulk copper, then you remove using a very, very fast process. Then you use a slightly slower process to remove all the remaining residual copper and stop on the barrier layer. So the process is designed to stop and slow down on the barrier layer. And the third process is you remove the barrier. The third step is you remove the barrier and stop in the liner to ensure that all the metal, all the barrier, everything is cleared from the field area. You cannot have any conductive material here, right? Because that will cause major performance and reliability problems with subsequent metal layers. And the key process parameters here, of course, are the polishing recipe, the process conditions, what force you use.
Last year.
Problem with the audio, or is it only for
Yeah,
me?
All of
looks like
those
yeah.
are removed.
Yeah.
Are removed from the surface. So key considerations for this process are cleaning off all the slurry and the residue, ensuring that there is no residual metal left anywhere on the top, on the dielectric surface, and minimizing and ensuring there are no scratches or particles left as well on either on the copper or on the dielectric. And last but definitely not the least, controlling the topography of the copper. I don't have those images here, but if your process is not correctly optimized, then you end up with defect modes like what we call dishing, where the copper in the TSV is recessed. Rather, it is thinner in the middle than on the edges, which can cause problems. Or what we call erosion, where an entire region of the die is thinned down more than the neighboring regions. So those are defect modes that are to be avoided. This shows you a top-down view and a cross-section of the TSV after CMP. So you can see it's very cleanly formed, right? You can see the copper surrounded by the dielectric. Moving on now from the front side processing to the VR reveal or the backside process. First, we start with backside silicon thinning. So here the wafer is temporarily attached to a carrier. And before you do any of thinning, you have to do something called edge trimming, right? So where essentially you trim, literally remove a portion of the silicon on the edge of the wafer. And the reason you do that is if you grind without doing the trimming, you're left with a very, very fragile knife edge on the wafer after grinding, which is very prone to breakage and can severely damage the wafer. Whereas if you do edge trimming, because you've already removed a large portion of the silicon here, by the time you finish grinding, you have a straight line, a flat straight line. And the grinding follows a three-step process. Basically, where you have coarse grinding, where you grind down to roughly around an average of 100 microns or so. Fine grinding, which is grinding close to the final thickness, and followed by a polishing process, which removes roughly 2 to 5 microns. And the goal of the final polish process is to remove any subsurface and surface damage and smoothen it. The grinding steps themselves are purely mechanical processes, where the grinding wheel actually acts like a point contact, like a tool bit almost, and shaves off large portions of the wafer surface in every pass. So you can see fast removal, high damage to the surface, and then you remove slowly, and the same which recovers the damage or heals the damage on the wafer surface. Next step is, once you've thinned it down, is to expose the TSVs themselves. This is done typically through dry etching or plasma etching. That etch process is highly selective to the oxide liner. Now, if you look here, you would remember, right, that an oxide liner is put before the TSV metal layers are put down. So when you etch down here, after thinning it down, the etch has to be very, very selective. So it stops on the oxide and does not punch through the oxide into the copper. And there are, of course, many dry etch inherently can be tuned to be selective that way to oxide. So some cases people talk about using wet etch, but as far as I know, the industry standard pretty much is a dry plasma etch. So it's performed, it's highly selected to the oxide, and it ensures that the copper continues to be covered and protected by the liner oxide. And so you can see these TSV pillars jutting out above the backside silicon. So this is a very critical process. And controlling the height of these pillars, the uniformity, is extremely critical. And that height variation essentially is the sum of the etch variation, the thinning itself, the wafer thinning, and of course the original variation of the TSV trenches themselves when they were formed to begin with at the beginning of the via metal process. And if your edge reveal is too little, then the TSV will get buried under the subsequent oxide layers that are deposited and will not be exposed. So those TSVs will be dead, will not become through silicon ever. If you have too much reveal, then your too high a structure is jutting out and it exposes the TSV to risk of breakage. So controlling your process uniformity is extremely critical.
So Uday, just one question on the previous slide. Yeah. So as we know, for example, this like SF6 based plasma, right? It is always have some kind of a uniformity issue from the wafer edge to center, and especially on a 300 millimeter platform. Even if we consider, let's say, 1% uniformity, it is always going to have something about 5 to 7 micrometer of difference. So how does the industry compensate for that variation?
Well, how old is your data about that talks about this 5 to 7 micron variation? Is that the latest?
So let's imagine that we have a wafer thickness of starting, let's say 700 micrometer, correct? Right.
Okay.
Even if we consider, for example, 1% variation from the edge to center, which is a normal one, because in 300 millimeter wafer platform, the controlling the plasma distribution is going to be very difficult task, right? So I'm assuming 1% variation. What is the current, or maybe you can indicate me, what is the current variation in the etch rate versus like from the edge to center?
It's been a while, so I forget the exact number. What I do know is firstly, I think your assumption is the wafer is 700 microns thick, right? At this stage, it is more like 50 to 100 microns thick.
Yes,
right?
fine.
You thin down the silicon. So your net amount of silicon to be removed is a lot less than 700 microns.
Okay.
And uniformities, I do not remember, to be honest, because the information I have is also now a few years old. And I'm sure a lot of improvement has gone on in these last 2 years because this is running in high volume production, right? So
so typically they are using this fluorine plasma, right? So people have explored SF6 and also this NF3, which will probably do better uniformity thing. But I understand that controlling the plasma distribution over a large substrate is always going to be a challenging task. And there's no matter what you do on the center portion, there's always going to be having a little bit higher etch rate compared to the center portion. Yeah, edge is always having the higher part. So that is one of the major tasks, major difficulties in this particular domain, how to control the etch. So
yes, it is. Right. That's why it's a challenge that I also brought up. You have to be very careful how you modulate, how you ensure that your TSV height variation after the etch is as little as possible.
Yeah. And one more thing, if I may ask, you said something about wet chemical etching, right? So is it going to be something like a EDP kind of etching or something else?
Well, the studies that I have seen, people use some things like TMAH, for example, right?
But TMH will give you anisotropic etching, right? It is going to be crystal plane dependent etching behavior. But here, when you are doing this kind of wet chemical etching, you want to make sure that
That it is isotropic. Yeah.
Yeah. So that's why I was curious about the wet silicon etching. Yeah.
Hey, Pradeep, Venki here.
Yeah.
Typically in current production, there are steps to use protective layers for edge stop. So that's how they address the variation issue.
Yeah.
Yeah. So here the oxide layer is the etch. The TSV liner is the natural etch stop that is used, right? But I think the point is still valid that the silicon around this will continue to be etched, right? So controlling that uniformity center to edge is of course very, very critical, right? And I think someone who is a unit process expert on etch would probably be better placed to answer where we are right now in this.
Because my previous experience with EDP was, it was, for example, when you do like spin kind of etching method, it always going to have a little bit of amount of problematic thing. But anyway, we can discuss later maybe.
Yeah. So let's move on. Yeah, let's move on. Yeah.
Okay. Thank you for the question. Good insights. Then we move on to interlayer dielectric deposition, right? Which is shown here, where essentially you deposit a low temperature silicon nitride and followed by a thicker silicon oxide layer. So the nitride acts as a moisture barrier and a copper diffusion barrier, and SiO2 provides the electrical insulation between the TSV and the surrounding flat wafer surface, and also stress buffering. So here conformal deposition is critical so that you don't have formation of seams at the corner, as you can see here in this sample illustration. Conformal and then thickness uniformity also is critical, and to ensure that you don't deposit too much oxide, because when you go to the next step, which is the dielectric polishing or CMP, where the copper is exposed, you have to ensure that all the TSVs are revealed. So if your oxide is too thick and the TSV pillar before oxide deposition has not been revealed enough in the upstream etch process, that TSV could end up being buried under the oxide and not revealed through polishing. And I don't have images here, but they're easily available online. And if the TSV is jutting up too high, then during this polishing process, you could end up breaking it off as well because of too much stress on a protrude structure. But if all goes well, if the process is well-tuned, uniform, this is what you end up with. As TSVs are flush with the field oxide. Here you can see the TSV, you can see the liner around it. And the wafer is now ready for downstream processing.
Then we need to bring it to a close. Okay.
Yes, this is the last slide.
Next slide. Yeah. Okay, good. Yeah. Okay, good. Thanks.
So this is what is on the front side and back side processing is completed. You have, after the backside processing is done, you can put down the redistribution layers, do all other kinds of interconnections if you like, and the wafer can go on to the next process. You can either debond the wafer or send it down for further packaging operations. So with that, come to the end of my talk. Thank you once again, everyone, especially Professor Rao, for the opportunity. And if there are any last-minute questions, glad to take them.
Thank you. Thank you so much, Uday. Okay, so let's entertain 2 questions, please, for the next few minutes. Any questions to Dr. Uday on any of these things you talked about?
I have one question, was regarding the scaling. So as Dr. Uday mentioned that we're going to ruthenium, right? Do you see ruthenium to play a critical role here? And what are your views regarding the scaling here? So I know 1:10 is typical aspect ratio, but in terms of wafer thinning and then TSV scaling, so from like 5 micron to 1 micron, or do you think it's going to even go lower than that?
Well, one itself will be pretty challenging, right? But I think as we go more and more as advanced packaging becomes critical to keeping the device performance roadmap going, but we will have to migrate to TSVs that are of that order of magnitude of dimensions, right? And their processes like this ruthenium deposition will become key, because there is no way PVD can work at a 1/20
aspect ratio. Yeah.
aspect ratio. Right? It'll just pinch off the top, and you will not get
Yep.
any coverage at the bottom of the trench or the sidewalls.
Good point.
I have
Okay,
another
let's go to
question.
This question is
go
from
ahead.
Akash Bhatnagar. Dr.
Yeah,
Akash.
Akash.
Hi, Uday. Thank you so much for your talk. This is Akash from Short Glass in Mines. I was just curious because you mentioned about the role of TSVs as for power delivery and as heat sinks, but then do you expect different kind of aspect ratios for these two kind of applications for TSVs? When they are being heat sinks or whether they are being used for power deliveries?
Yes. So, from my understanding, those structures are typically larger, at least than your signal delivery TSVs.
Okay.
Correct.
Mhm.
Thermal
But these
TSVs
differences
are
are like they are like double the size, or they are like, I mean, do we have any fixed ratios here between TSVs, between power deliveries and TSVs being used as heat sinks?
I don't know if there's a single design rule that applies, right? So that
Okay.
is something I couldn't really tell you.
Okay.
Yeah, I have
Thank
a
you.
question. So whatever you explained, Dr. Uday, as well as also Professor Rao, that in India, whatever we are planning for IDSPS, right? So how much close we are in India for this type of technologies to be developed and worked on?
From my perspective, okay, TSVs have been developed and have been in production a long time. But we want to learn and apply these techniques to make what we call TGVs, through glass vias, through package vias, very small, exactly, okay, similar reasons, similar processes, somewhat similar materials, on a large panel. So Professor Pradeep Dixit is planning to work on that by setting up a center and a lab at IIT Bombay for basic research in this area. We expect to set up a pilot line using Rubias in glass, learning from the TSVs and applying them. So those are our plans.
Okay.
Those are our strategic plans to make it happen. Yeah.
Thank you.
Okay, we need to stop in here. Okay, thank you very much for taking the time. Thank you, Professor Uday. You fantastic summary of the whole program. Yeah, appreciate that. So we'll circulate the slides appropriately, particularly for the faculty and our industry partners. Okay, and so this is fascinating, wonderful. So let me get back with you with the next few days to talk about some of this stuff.
Sounds good.
Thank you. Yeah,
Thanks,
thank you,
Dr. Rao.
Kumar, for making
Thanks all.
Yeah, thank you. Thank you all. Thank you all. See you. Bye.
Thank you. Bye-bye.
Bye-bye.
Bye.
Good night. Bye.